In this video, we're going to do an example involving the cheapest link algorithm. So recall that the cheapest link algorithm takes as an input a complete weighted graph, and the output of the algorithm is a Hamilton circuit. Now, the Hamilton circuit that it produces is not necessarily the one of least total weight, so it won't always give us a solution to the traveling salesman problem, but it will give us an approximate solution. The cheapest link algorithm proceeds in the following manner. First, you take all the weights and you make a list of the weights from largest to smallest. So the smallest weight is 2, followed by 3, then 4, 5, 7, 8, 9, 10, 11, and 13. And now we go to the cheapest edge that we have not used yet, and we ask whether it satisfies the following two constraints. The first constraint is that choosing the edge should not form a circuit too early. By the time we're completely done with the algorithm, we should have a Hamilton circuit, but we do not want to have a circuit before that point. We don't want to have a circuit involving only 4 vertices or only 3 vertices. We want to involve all 5 vertices. So we don't want a circuit too early. The other constraint we want to satisfy is that if you choose the edge, we should not have 3 chosen edges coming out of any given vertex. And if you think of a Hamilton circuit, you'll only ever have 2 edges coming out of every single vertex, right? You're going to use a Hamilton circuit is a circuit in which every single vertex is used, but you'll only ever have 2 edges coming out of a given vertex. You'll never have 3 or more. So in this list here, we see the cheapest edge that hasn't been used is 2, because we're just starting out. So there's no problem with choosing 2. We simply select it, and in the list, let's put a check mark next to it to indicate that we've actually used it. And then we go to the next cheapest unused weight, which is 3. And again, there's no problem here. If we select 3, we're not forming a circuit too early, and we're not having 3 chosen edges come out of a single vertex. One thing to notice here is that as I'm choosing edges, so for example, the first edge I chose was the one labeled by 2, and the next one was the one labeled by 3. These edges didn't have to connect, right? These 2 chosen edges don't connect to each other at this point. So in the cheapest link algorithm, there's no need for the edges to connect to each other. All that's necessary is at the very end they eventually form a circuit. But before you get to the end, the different edges may not connect up. The next cheapest edge is 4, and so we can look at this edge, and we note that if we chose it, there's no problem. We do not form a circuit, and we don't have 3 chosen edges coming out of a vertex. The next edge is 5. Now notice if you chose 5, what would happen? If we chose 5 here, then we would get a circuit. We would get a circuit involving E, B, and C, and so that would be forming a circuit too early. We wouldn't have a circuit involving all 5 vertices. So we can't use the edge 5. It doesn't satisfy our constraints, so we're going to put an X next to it, and we don't color it in this case. And now we go to edge 7, and there's no problem there. It satisfies both our constraints. Now we go to edge 8. Now notice if we chose edge 8, we would have a circuit involving D, C, B, and A. So we'd form a circuit too early. We wouldn't have a circuit involving all 5 vertices, so we can't use edge 8. What about 9? If you choose 9, you should be able to see that you're going to form a circuit involving D, B, and A. So again, we don't want that. Now the next is edge 10. You can see that if you chose edge 10, you would have a circuit involving E, A, B, and C. So just 4 vertices. So again, we can't use edge 10. Now if we look at edge 11, we can see, well, we wouldn't have 3 chosen edges coming out of any vertex. We would form a circuit, but it would be a circuit involving all 5 vertices. So if you kind of look at this, think of starting at E, for example. From E, we could go to C, and then B, and then A, then D, and back to E. So that would be a circuit, but it's a circuit involving all 5 vertices. So it's a Hamilton. And finally, there's only one weight left, 13, but at this point we already have our Hamilton circuit, so there's no need to proceed. We don't care about that edge. In this case now, we have found a Hamilton circuit. So if we want to list this circuit, we could start anywhere we wanted, right? That doesn't make any difference. So we could think of starting at E, and then we could go to C, and then to B, and then A, and D, and back to E. So this is one way to represent the circuit. There's other possible ways that we could represent this. We could read this backwards. We could have started in another vertex instead of E. We could have started at A. It doesn't matter. It's the same Hamilton circuit. This is the solution that the cheapest link algorithm provides. Remember that this need not be the Hamilton circuit of least total weight, but it is an approximate solution.